Right now you are living inside the brightest moment the universe will ever know. Not the most energetic, not the largest, not the oldest, but the brightest. The era in which stars burn. The era in which galaxies spiral with light. The era in which matter has organized itself into structures complex enough to look upward and ask questions. You are standing at the peak of cosmic luminosity in the narrow window of time when the universe is still alive with fire and you do not even know it. Here is what most people get wrong when they think about the end of everything. They imagine a catastrophe, an explosion, a collapse, a sudden moment of violence that closes the curtain on existence. They picture fire or ice or some boundary wall rushing toward the cosmos at the speed of light. They imagine an ending that looks like an ending, dramatic, final, unmistakable. The truth is far more devastating than that. The universe will not end in fire. It will not end in ice. It will end in silence, so complete in darkness, so absolute in cold, so total that the very concept of an ending will have no witness to observe it. There will be no final explosion. There will be no last light that flickers and dies. There will only be a slow, patient, indifferent unwinding, a process so gradual that 1 trillion years will pass between each recognizable change, and the change itself will be imperceptible because there will be nothing left with eyes to perceive it. This is the story of how the universe dies. Not quickly, not dramatically, but completely, irreversibly, and with a patience so vast that every civilization that has ever existed, every star that has ever burned, every galaxy that has ever spiraled through the dark, all of it will come to represent nothing more than the very first moments of a story whose final chapters will not be written for a length of time so incomprehensible that human language has no honest way to contain it. If you find yourself drawn to journeys that completely reshape the scale of what you thought was possible, that leave you sitting quietly afterward, staring at the ceiling, reconstructing everything, do something small for this channel. Hit the like button, subscribe. It takes seconds, and it genuinely matters. It allows these stories to reach other people who might need them. And now get yourself comfortable. Let the world outside go quiet. Because what comes next will require your full attention, and it will be worth it. Let's begin. To understand where the universe is going, you first need to understand where it stands right now. And to do that, you need a new way of measuring time. The numbers involved in the death of the universe are so large that the ordinary calendar becomes useless. 1 billion years is already difficult enough to picture. 1 trillion years is simply the word trillion attached to the word years, floating in the mind without real weight. So cosmologists have developed a different scale. They measure time in what are called cosmological decades. A cosmological decade is not 10 years. It is a power of 10 years. Cosmological decade 1 is 10 years. Cosmological decade 2 is 100 years. Cosmological decade 10 is 10 billion years, approximately the current age of the universe. This scale is the only honest way to navigate the timeline of everything. Right now, the universe is approximately 13.8 billion years old. In the language of cosmological decades, we are somewhere between decade 10 and decade 11. The Big Bang happened at decade 0. The first stars ignited around decade 8 or 9. Our sun was born at decade 10. And the era we are living in right now, the era of stars, of burning hydrogen, of light pouring across galaxies, this era will continue until roughly cosmological decade 14. That is 100 trillion years from now. Pause with that number for a moment. 100 trillion years. The current age of the universe, all 13.8 billion years of it from the Big Bang to this moment, from the first particles to the first galaxies, to the rise of life on Earth, represents less than 1/100th of 1%. All of the time that stars will continue to burn before the last one goes dark. Everything you have ever heard about cosmic history, every discovery, every civilization, every story told under the light of a sun has happened in what amounts to the opening breath of a story that will take 100 trillion years just to reach its first major silence. This era, the era we inhabit, has a name. Cosmologists call it the stelliferous era, from the Latin word for star-bearing. It is the age of stars, and to understand what it means for this age to end, you need to understand what a star actually is and what it costs to remain one. A star is a negotiation. On one side of the negotiation is gravity, the relentless inward pull of a mass so large that the atoms at its center are crushed together at pressures and temperatures beyond anything that exists naturally on Earth. On the other side is nuclear fusion, the process by which hydrogen nuclei are forced together to form helium-releasing energy in the form of light and heat that pushes outward against the crush of gravity. A star exists only while this negotiation is ongoing. The moment the fuel runs out, the negotiation ends and gravity wins. Our sun has been burning for approximately 4.6 billion years. It has enough hydrogen remaining to burn for another 5 billion or so. By the standards of the cosmos, it is a middle-aged star, not young, not old, somewhere in the comfortable middle of its life. When it exhausts its hydrogen, it will swell into a red giant, engulfing the inner planets, then collapse into a white dwarf, a dense hot remnant, roughly the size of Earth, slowly cooling over billions of years. But our sun is not typical of all stars, and this distinction matters enormously for the fate of the stelliferous era. The smallest stars in the universe are called red dwarfs. They are dim, cool, miserly with their fuel. Where the sun burns through its hydrogen in 10 billion years, a red dwarf stretches the same process across hundreds of billions of years, some of them trillions of years. They are the tortoises of the stellar world, slow and patient beyond imagination. A red dwarf named Proxima Centauri, the nearest star to our sun, at a distance of 4.24 light-years, will still be burning long after our sun has cooled into a dark cinder. It will burn for another 4 trillion years. 4 trillion years. If you shrank the entire age of the universe to a single day, 24 hours from the Big Bang to right now, then Proxima Centauri has not even finished its first hour. It has barely begun, and it is not alone. The galaxy is full of red dwarfs. Estimates suggest they make up roughly 70 to 80% of all stars in the Milky Way. The vast majority of the stellar population is not burning fast and bright like our sun. It is burning slow and dim, stretching its lifetime across timescales that dwarf everything we have discussed so far. This is why the stelliferous era extends to cosmological decade 14. The red dwarfs will keep going long after every star like our sun has died. Long after every massive, brilliant blue star, those profligate giants that burn through their fuel in mere millions of years and explode as supernovae has come and gone. Long after the Milky Way has merged with the Andromeda galaxy, a collision that will happen in approximately 4 billion years and will be less a catastrophe than a slow rearrangement. The two galaxies passing through each other like clouds, their stars almost never actually colliding because the distances between individual stars are so vast. Long after all of that, the red dwarfs will still be burning. Imagine standing in a galaxy 1 trillion years from now. The sky would look different to you in profound ways, and yet it would also still be recognizable as a sky full of stars. The brilliant blue giants would be long gone. The sun-like yellow stars would have become white dwarfs. But the red dwarfs would still be there, dim, ruddy points of light scattered across the dark. The galaxy would be quieter, cooler. The rate of star formation would have slowed dramatically, because the raw material for new stars, the gas and dust clouds that collapse under gravity into new stellar nurseries, would be running out. The universe does not replenish its hydrogen. What was present at the Big Bang is what there is, and over time it gets locked up in stellar remnants, used up by fusions scattered into forms that cannot easily collapse back into new stars. New stars would still be forming 1 trillion years from now, but rarely, occasionally, like the last few fires in a dying city lighting up briefly before going dark. The process of star formation in the universe peaked approximately 10 billion years ago. We are already on the declining slope. The universe is not at the beginning of the end of its stellar era. It is past the halfway point. It has already moved through its most productive epoch and is coasting now on the remaining fuel of the red dwarfs, those long burning embers whose patience exceeds comprehension. But even their patience has limits. 100 trillion years from now, cosmological decade 14, the last red dwarf will exhaust the last of its hydrogen. There will be no supernova. There will be no dramatic finale. A red dwarf does not explode when it dies. It simply fades. The fusion reactions slow. The light dims, the temperature drops, and the star, which may have been burning since before our solar system existed quietly, ceases to be a star. It becomes a black dwarf, a cold, inert sphere of degenerate matter, no longer fusing, no longer radiating, simply drifting in the dark. Picture the moment after the last red dwarf goes out. There is no announcement, no sound. The universe does not mark the occasion. One moment, there are stars, dim, reddish, but burning. The next moment, there is one fewer, then another, then the last. The stelliferous era ends not with a bang but with a cooling, and the universe crosses a threshold that nothing will ever undo. The age of stars is over. Every star that will ever burn has burned. Every sun that will ever rise over any world has risen and set for the last time. What remains is a universe of remnants, white dwarfs slowly cooling toward absolute zero, neutron stars spinning in the dark, their pulses growing fainter with each passing billion years. Black holes, those final inheritors of stellar death lurking at the centers of galaxies, patient beyond all measure, waiting for matter to fall into them. And between all of these objects, vast stretches of space so empty that the distance between any two particles of matter is greater than the observable universe is today. The stelliferous era gave the universe everything it needed to become complex. Stars forged the heavy elements, carbon, oxygen, iron, gold, that planets are made of. They warmed worlds enough for liquid water to exist. They provided the energy gradients that chemistry could exploit. In some extraordinary places, that chemistry became biology. That biology became thought. That thought looked up at the stars and began to wonder. All of that happened here in this era, in this narrow window of cosmic time. We are the children of the stelliferous era, born in its last quarter, burning briefly in the light of stars that will not exist for much longer, not on cosmic timescales. Our sun has 5 billion years remaining, which sounds like eternity until you place it against the 100 trillion years that the era itself spans. On that scale, 5 billion years is less than 1 month in a human lifetime. We are not early, we are not late, but we are mortal in a way that encompasses not just our individual lives, not just our civilization, not just our species, but our entire stellar neighborhood. The sun will die, and when it does, it will join the long silence that is already beginning at the far ends of the stellar distribution, where the dimmest stars are already starting to cool. But understand this clearly: the death of the last star is not the end of the story. It is not even close to the end. When the final red dwarf goes dark at cosmological decade 14, the universe will still have the overwhelming majority of its existence ahead of it. The stelliferous era, 100 trillion years of stars and light, and the possibility of warmth will turn out to be the briefest of preludes, a spark before a darkness of duration so immense that 100 trillion years placed against what follows will seem like the first fraction of a second in a film that runs for 1 billion years. The Degenerate Era is next, and it will last so long that by the time it ends, the concept of a star will be as ancient and inaccessible as the Big Bang is to us now. The universe after the last star is not empty, not yet. When you picture darkness, you probably picture nothing, a void, a vacancy, an absence of everything. But the darkness that follows the stelliferous era is not that kind of darkness. It is a darkness crowded with objects, dense, massive, silent objects drifting through space at vast distances from one another, cooling slowly over timescales that make the age of stars seem like an afternoon. The universe after cosmological decade 14 is not a void, it is a graveyard, and like all graveyards, it is full. The most numerous residents of this graveyard are white dwarfs. A white dwarf is what most stars become after death, including our sun billions of years from now. When a star like the sun exhausts its hydrogen and swells into a red giant, it eventually sheds its outer layers into space, leaving behind its compressed core. That core is a white dwarf, a sphere roughly the size of Earth but containing approximately the mass of the sun composed primarily of carbon and oxygen, squeezed into a state called electron-degenerate matter. It is no longer fusing. It is no longer generating energy through nuclear reactions. It is simply a hot ember radiating the heat it accumulated during its life, cooling toward the temperature of the surrounding space. At a rate so slow, it borders on the geological. A newly formed white dwarf may have a surface temperature of 100,000 degrees Kelvin. Over billions of years it cools. Over hundreds of billions of years it cools further. The Uises. At its coises, every voices is not yet old enough for any white dwarf to have cooled completely to the temperature of the surrounding space. Every white dwarf that has ever formed is still warm, still faintly glowing. In the infrared, if you had the right instruments, you could see them dim reddish points scattered across the galaxy, the cooling embers of a billion dead suns. But given enough time, and the Degenerate Era has time in quantities that make generosity seem stingy, even white dwarfs will finish cooling. At some point many trillions of years from now, the white dwarfs will have released all their stored heat. They will reach thermal equilibrium with the surrounding space. They will become black dwarfs, objects that are in every practical sense dark. Not quite at absolute zero, but close enough that the distinction is academic. They will still exist. They will still have mass. They will still exert gravity. But they will emit no light detectable by any instrument we can currently imagine. They will be present in the universe, the way a stone at the bottom of a dark ocean is present, real, massive, entirely invisible. Here is the extraordinary thing about black dwarfs. None exist yet. Not a single one. The universe is not old enough. The cooling time required is longer than the current age of the cosmos. Every white dwarf ever formed is still in the process of cooling. The black dwarfs are coming, but they have not arrived. They are a feature of a future so distant that our sun has not yet even begun to die. The universe is still in its first chapter, and the black dwarfs are a phenomenon of the middle chapters, chapters that will not begin for longer than the universe has currently existed, multiplied many times over. Now, hold all of this in mind and consider the scale of what the Degenerate Era contains. At cosmological decade 100 trillion years from now, the stellar era ends. What remains is a universe populated by white dwarfs cooling toward black dwarfs, neutron stars spinning in the dark black holes, anchoring the remnants of galaxies, and the occasional brown dwarf objects too small to ever ignite into stars. Failed suns drifting cold and dim through the void. Between all of these objects stretches space that is almost incomprehensibly empty. The distance between any two stellar remnants will be on average larger than the distances between stars today. The galaxies themselves, those vast collections of hundreds of billions of stars that define the visible universe at this moment, will have changed beyond recognition. Let us follow the Milky Way forward in time. In approximately 4 billion years, our galaxy will begin its merger with the Andromeda Galaxy, a collision that astronomers have already confirmed through measurements of Andromeda's approach velocity. The word collision is misleading because the stars within both galaxies are so widely spaced that almost none of them will actually impact one another. The two galaxies will pass through each other like two clouds of cigarette smoke merging in a still room. Gravity will reshape them. Tidal forces will draw out long streams of stars. Over a period of hundreds of millions of years, the two spiral galaxies will distort, stretch, overlap, separate slightly, fall back together, and ultimately merge into a single elliptical galaxy that astronomers have already named Milkomeda. By cosmological decade 14, when the last star dies, Milkomeda will have long since settled into its final form. The dramatic spirals will be gone. The bursts of star formation triggered by the merger will have exhausted themselves and faded. What remains will be a vast elliptical cloud of stellar remnants, slowly dispersing as gravitational interactions eject individual objects outward, and the central black hole, a monster formed from the merger of the Milky Way's Sagittarius A times and Andromeda's own supermassive black hole, settles into quiet dominance at the center. Around cosmological decade 17, that is 10 million billion years from now, something remarkable will have happened to most of the stellar remnants in the galaxy. They will be gone, not consumed, not destroyed. ejected. The process is called gravitational evaporation, and it is one of the strangest and most patient phenomena in all of astrophysics. In any system where many masses are interacting gravitationally, a galaxy, a globular cluster, a collection of stellar remnants, occasional close encounters between objects, transfer energy between them. Over immense timescales, these interactions cause some objects to gain energy and some to lose it. The objects that gain enough energy eventually reach escape velocity and are flung out of the system entirely ejected into intergalactic space to drift alone forever. The objects that lose energy sink inward, falling toward the center. Eventually, most of the mass of the system either escapes outward or falls inward into the central black hole. By cosmological decade 17 to 19, most stellar remnants that once made up the Milky Way will have been flung into the deep intergalactic void or swallowed by the central black hole. The galaxy as a coherent structure will have ceased to exist. What remains will be isolated objects, lone white dwarfs, lone neutron stars, lone black holes, drifting through a space so empty that the nearest neighbor of any given object may be millions of light years away. The universe at this stage is unimaginably lonely. But there is something else happening during the Degenerate Era that operates on an even longer time scale and whose outcome is genuinely uncertain. Uncertain not because we lack the will to calculate it, but because the experiments needed to resolve the question have not yet given us a definitive answer. The question is this: do protons decay? A proton is one of the fundamental building blocks of ordinary matter. It sits in the nucleus of every atom. It is, along with the neutron and the electron, one of the three particles that make up everything you can touch, see, taste, or measure. Protons are extraordinarily stable. In the laboratory, we have measured their lifetime to be at least 10 to the 34 years. That is a 1 followed by 34 zeros. By any practical measure, protons are permanent, but certain theories in physics, grand unified theories, which attempt to describe all the fundamental forces within a single mathematical framework, predict that protons are not truly permanent. They predict that protons can, with extraordinary rarity, spontaneously decay into lighter particles. A proton decays into a positron and a neutral pion. The pion itself almost immediately decays further into gamma rays. The process is governed entirely by probability, and for any individual proton, the wait is extraordinarily long. But if protons do decay, if those theories are correct, then the Degenerate Era has a hard deadline. At around cosmological decade 37, even the most stable atomic nuclei will have had time to decay. Every proton in every white dwarf, in every black dwarf, in every planet, in every fragment of rock drifting through intergalactic space will eventually undergo spontaneous decay. The matter that makes up those objects will dissolve particle by particle into radiation and lighter particles. The black dwarfs will not survive to cool completely. The neutron stars will gradually lose their mass. The planets, all the planets, not just ours, but every world that has ever formed around every star in the observable universe, will dissolve into a faint haze of positrons and gamma rays. At cosmological decade 37, if proton decay occurs, there will be no more atoms anywhere in the entire observable universe. This is not a violent death. It is a slow dissolution. An atom that has existed since the early universe passed through countless stellar interiors, been incorporated into planets and organisms and rocks and oceans, will simply one day spontaneously transform. The proton at its center will decay. The electron will eventually annihilate with a positron. What was once a carbon atom or an oxygen atom or an iron atom becomes radiation photons spreading outward into an increasingly cold and empty universe, carrying with them the last information about the structure that once existed. If you were somehow present to observe a black dwarf during this era, hovering safely at a distance watching, you would not see it explode. You would not see it crack or shatter. You would see it do something far stranger and far more melancholy. You would watch it grow slightly dimmer over incomprehensible timescales as the faint glow of proton decay radiation, the last energy those atoms will ever release, radiates away from its surface. The black dwarf would shrink imperceptibly slowly, Its mass would decrease proton by proton over timescales of cosmological decades, and eventually it would be gone. Not collapsed, not exploded, dissolved, returned to radiation and dispersed into a universe that no longer has any use for it. Everything you have ever touched, every mountain, every ocean, every grain of sand, every human body that has ever existed, all of it is made of proton. If proton decay is real, then at cosmological decade 37, the last proton in the observable universe will decay, and ordinary matter, the substance of stars and planets and life, will have ceased to exist. But here is the profound uncertainty at the heart of this scenario. We do not know if protons decay. Experiments designed to detect proton decay, massive underground tanks of water, or other materials surrounded by sensitive detectors, waiting for the faint signal of a single proton's transformation, have been running for decades. The most sensitive of these, the Super Kamiokande detector in Japan, has watched trillions of protons for years and has not yet detected a single definitive decay event. This has not proven that proton decay is impossible. It has only pushed the lower limit of the proton's lifetime higher and higher. The experiments constrain the theories ruling out some versions of grand unified theories, while leaving others intact. The answer may come in the next decade with larger, more sensitive detectors, or it may remain elusive for generations. But the stakes of the answer are as high as any question in physics. If protons decay, the fate of matter is sealed on a timescale of cosmological decade 37. If they do not, the black dwarfs and neutron stars may persist far longer, dark, cold, inert, but present as the universe enters its next and most austere phase. Either way, something else is waiting. Something that does not care about proton decay. Something that is not made of ordinary matter at all. Something that has been present since the universe was young, growing slowly, patiently, feeding on whatever falls within its reach. The black holes have been here all along, and their era is about to begin. 1650, Claude responded. By the time the black hole era begins, the universe will have forgotten almost everything it once was. By the time the black hole era begins, the universe will have forgotten almost everything it once was. The stars are gone. The planets are gone. The galaxies, those vast spiraling collections of hundreds of billions of suns that define the visible universe in every photograph you have ever seen of deep space, have long since dispersed their constituent objects, either flung into the intergalactic void or swallowed by the massive objects at their centers. If proton decay is real, then even the atoms are gone, dissolved into radiation that has long since spread and cooled and thinned into irrelevance. The universe at this stage is not dark the way a room is dark when the lights go out. It is dark the way the inside of a stone is dark, absolutely, completely, with no memory of light, no surface for light to reflect, from no eye to receive it, even if there were. What remains are the black holes. Not many of them relative to the number of stars that once existed, but they are here, anchored at the centers of what were once galaxies, drifting alone through intergalactic space where they were flung during the gravitational evaporation of their host systems. Some of them are small stellar mass black holes formed from the deaths of massive stars, with masses ranging from a few times to a few tens of times the mass of our Sun. Some of them are intermediate, and some of them are the supermassive black holes that once sat at the hearts of galaxies, monsters containing millions, hundreds of millions, or even billions of solar masses, forged over cosmic time through the accretion of gas and the mergers of smaller black holes across the long history of the universe. The black hole at the center of the Milky Way Sagittarius A times currently has a mass of approximately 4 million times the mass of our Sun. The black hole at the center of the galaxy M87, famously photographed in 2019 by the Event Horizon Telescope collaboration, in the first direct image of a black hole's shadow, has a mass of approximately 6.5 billion solar masses. These objects are not curiosities at the edge of physics. They are the dominant structures of the universe's future. They are the last things that will ever exist, with coherent form, with defined boundaries, with mass concentrated in a specific location in space. And they are dying. Not quickly, not violently, not in any way that could be called dramatic on a human timescale, or even on the timescale of stars or galaxies or the entire stelliferous era. They are dying with a patience so extreme that the word patience fails to carry the meaning. They are dying through a process so slow, so faint, so quiet, that detecting it requires instruments of sensitivity. We do not yet possess instruments that would need to be pointed at a black hole in a universe with no other sources of radiation to contaminate the signal. The process is called Hawking radiation, and it is one of the most profound and consequential predictions in the history of physics. In 1974, a 32-year-old theoretical physicist named Stephen Hawking, already battling the motor neuron disease that would eventually confine him to a wheelchair for the rest of his life, published a calculation that astonished the physics community. He showed that black holes are not in fact perfectly black. They are not perfectly cold. They are not perfectly stable. They emit radiation. Slowly, faintly, almost imperceptibly, but they emit it. And in doing so, they lose mass. Over time, a black hole that emits Hawking radiation and does not accrete new mass will shrink. Slowly, then faster. Then in a final burst of energy, it will evaporate completely. The mechanism behind this prediction is subtle and extraordinary. It involves quantum mechanics, the physics of the very small and general relativity, the physics of the very large, in a way that neither theory alone can fully describe. Near the event horizon of a black hole, the fabric of space-time is so severely warped that quantum effects become significant. In quantum field theory, what we call empty space is not truly empty. It is a seething sea of virtual particle pairs, particles, and their antiparticles that spontaneously appear and annihilate in intervals so brief that they cannot be directly detected. In ordinary space, these pairs appear and vanish without consequence. But near a black hole's event horizon, something different can happen. One particle of a pair can fall inside the horizon while the other escapes. The escaping particle carries energy away from the black hole, energy that, by the conservation laws of physics, must come from somewhere. It comes from the black hole's mass. The black hole loses a tiny, almost incalculably small amount of mass with each such event, and it radiates a tiny, almost incalculably faint spectrum of thermal radiation, Hawking radiation, to the outside universe. The temperature of this radiation is inversely proportional to the mass of the black hole. A small black hole is hotter. A large black hole is colder. The supermassive black holes that anchor the remnants of galaxies are so cold that their Hawking radiation temperature is a fraction of a degree above absolute zero, far colder than the cosmic microwave background radiation that currently fills the universe at approximately 2.7 Kelvin. In the current universe, a black hole cannot even lose mass through Hawking radiation because the surrounding radiation field is hotter than the black hole and energy flows into it rather than out. But the universe is cooling. The cosmic microwave background, the afterglow of the Big Bang, a faint bath of microwave radiation that permeates all of space, is cooling as the universe expands. It was released approximately 38,000 years after the Big Bang, at a temperature of roughly 3000 Kelvin. Today it has cooled to 2.7 Kelvin. In the far future, it will cool further and further, approaching, but never quite reaching absolute zero. At some point trillions of years from now, the temperature of the cosmic microwave background will drop below the Hawking temperature of even the largest supermassive black holes. At that moment, the balance tips. The black holes will begin to radiate more energy than they absorb. The net flow of energy will be outward, and the evaporation, imperceptible as it is, will have begun in earnest. For a stellar mass black hole, say 10 times the mass of our Sun, the evaporation time is approximately 10 to the 67th years. That is a 1 followed by 67 zeros. To place this in the language of cosmological decades, it is somewhere around decade 67. Compare this to the current age of the universe at decade 10, and the entire history of the stelliferous era ending at decade 14, and you begin to feel the depth of the silence involved. A stellar mass black hole will outlast stars by a factor so large that the entire era of stars, 100 trillion years, represents an immeasurably tiny fraction of the black hole's lifespan. And yet, stellar mass black holes are the small ones. The evaporation time scales with the cube of the mass. Double the mass, and the evaporation time increases by a factor of 8. The supermassive black holes, those billions of solar mass monsters at the centers of galaxies, have evaporation times that stretch to cosmological decades approaching 100. A black hole with a mass of 1 billion solar masses will take approximately 10 to the 83rd years to evaporate. A black hole with a mass of 10 billion solar masses will take even longer. Picture the universe at cosmological decade 80. Every star that will ever burn has been dark for incomprehensible eons. The last white dwarfs cooled into black dwarfs and either dissolved through proton decay or still drift cold and inert through an empty universe depending on whether protons decay. The galaxies dispersed so long ago that no structure in the current observable universe has any memory of them. Individual black holes drift alone through a space so vast and so empty that two black holes could spend the entire current age of the universe drifting without ever coming close enough to interact gravitationally in any meaningful way. The universe at cosmological decade 80 is a place of almost perfect emptiness, populated by isolated black holes at distances from one another that are measured not in light years, but in numbers that have no convenient name. And each black hole is slowly, quietly emitting its Hawking radiation into the surrounding darkness. Radiation so faint, so cold, so tenuous, that detecting it would require an instrument larger than the observable universe. A faint thermal glow that is, for all practical purposes, indistinguishable from the background. But it is happening, particle by particle, quantum fluctuation by quantum fluctuation. The black holes are losing mass. The process is not uniform in its pace. As a black hole loses mass, it gets slightly hotter. As it gets hotter, it radiates slightly faster. It loses mass slightly more quickly. This creates a feedback loop, agonizingly slow at first, then gradually accelerating. For most of a black hole's evaporation lifetime, the process is nearly imperceptible. But in the final stages, something remarkable happens. In the last fractions of a second of a black hole's existence, the feedback loop has accelerated to the point of explosion. The final evaporation of a black hole is not a quiet fade. It is a burst. As the mass drops below a certain threshold, below the mass of a small asteroid, then below the mass of a mountain, then below the mass of a car, then below the mass of a human, the Hawking temperature climbs steeply. The radiation becomes more energetic. The evaporation accelerates. The remaining mass converts to energy in a final burst of gamma rays and other particles, an explosion that for its brief moment is energetic enough to be detectable across a significant fraction of the observable universe. Then it is over. What was once a black hole containing the mass of millions of suns, which formed in the collapse of the first massive stars which survived the death of stars and galaxies, and perhaps even the decay of all ordinary matter, releases its last energy in a flash that lasts less than a second. The information about everything that ever fell into it, all the stars, all the gas clouds, all the matter that crossed its event horizon over billions and trillions and quadrillions of years, is released in that final burst, encoded in correlations between the outgoing radiation in ways we do not yet fully understand. Then the black hole is gone. Not collapsed into something smaller, not transformed into a remnant. Gone, evaporated, returned to radiation. The space where it existed is now simply space, empty, cold, expanding, containing nothing but the fading echo of its final burst, spreading outward at the speed of light into a universe that has nothing left to illuminate. One by one, across cosmological decades that span from 67 to approximately 100, the black holes evaporate. The small ones go first, their final bursts brief and energetic. The intermediate ones follow over longer timescales. The supermassive black holes, those ancient monsters that have been present since the universe was young, that survived everything that outlasted atoms and stars and galaxies, go last. Their final evaporations are the last energetic events in the history of the universe. The last black hole to evaporate whatever supermassive remnant happens to be the most massive survivor will release its final burst at somewhere around cosmological decade 100, 10 to the 100th years. This number has a name. It is called a googol, 1 followed by 100 zeros. In a Google years, the last black hole will be gone. The universe will have lost the last structured object it will ever contain. After the final burst fades, after the last gamma rays from the last evaporating black hole have spread and thinned and redshifted toward longer wavelengths over millions of years of travel through expanding empty space, there will be nothing left to produce new energy. No fusion, no accretion, no proton decay, no Hawking radiation. The universe will contain only the remnants of all these processes, an extraordinarily dilute gas of photons, neutrinos, electrons and positrons, all at nearly identical temperatures, all separated by distances so vast that the probability of any two particles ever interacting again is effectively zero. The last story the universe will ever tell has been told. What comes next is not death exactly. It is something harder to name, something that has no precedent, no analogy, no human experience to map it onto. Something the universe has been moving toward since the first fraction of the first second after the Big Bang, as inevitable as the expansion of space itself. It is called the heat death, and it is not an ending. It is a stillness that will last forever. Claude responded, "The last gamma rays from the last evaporating black hole travel outward at the speed of light. The last gamma rays from the last evaporating black hole travel outward at the speed of light. They travel through a universe that has nothing left to stop them. No gas clouds to scatter them, no dust grains to absorb them, no atoms at all if proton decay has done its work, no planets, no stars, no galaxies, no structures of any kind. Just space expanding, cold, dark and silent in a way that goes beyond the ordinary meaning of silence. They travel for millions of years, then billions, then trillions, spreading and thinning and redshifting as the expansion of the universe stretches their wavelengths toward longer and longer values, draining their energy in the same patient way that the expansion has been draining the energy of the cosmic microwave background since the universe was young. Eventually, those last photons become indistinguishable from everything else. They join the background, the faint, cold, nearly uniform bath of radiation that fills all of space, the final inheritance of all the energy that has ever existed in any form, from the nuclear fires of the first stars to the accretion disks of the last black holes, to the quantum fluctuations that produced Hawking radiation across incomprehensible eons. All of it is still here, in a sense. All of it has been converted to radiation, to heat, to the random thermal motion of particles spread so thin across so vast a space that the universe is, for all practical purposes, at a single temperature. And that temperature is almost exactly zero. Not zero. Almost zero. The universe at this stage is not at absolute zero, and it will never quite reach it, because absolute zero is a limit that thermodynamics approaches but never achieves. But the temperature of the universe at cosmological decade 100 and beyond is so close to absolute zero, measured in fractions of a fraction of a Kelvin, in numbers that require scientific notation with negative exponents of staggering depth, that the distinction is academic. For any physical process that requires a temperature gradient to operate, for any engine, any chemical reaction, any biological system, any computation, any form of information processing whatsoever, the universe at this stage is functionally at absolute zero. This is what physicists mean when they speak of the heat death of the universe. The name is misleading. It sounds violent, it sounds hot, it sounds like something burns, but the heat death is the precise opposite of burning. It is the state in which heat, in the thermodynamic sense, meaning the capacity of energy to do work, to drive processes, to create change, has been completely and irreversibly distributed. The universe has reached thermodynamic equilibrium. Every region of space is at the same temperature. Every particle has on average the same energy as every other particle. There are no gradients, no differences, no places where energy is concentrated and other places where it is not. And without gradients, nothing can happen. This is the deep truth behind the heat death, and it requires a moment of careful thought to fully absorb. The universe does not run on energy alone, it runs on differences in energy. A fire does not simply release heat, it releases heat into a cooler environment, and it is the difference in temperature between the fire and its surroundings that allows work to be done, that allows engines to run, that allows life to metabolize, that allows thought to occur. Remove the difference, make the fire and its surroundings the same temperature, and the fire still contains the same amount of energy it always did. But nothing can extract that energy anymore. Nothing can use it. It is present and inaccessible simultaneously, like wealth locked in a vault, whose combination no one knows and whose walls no force can breach. The universe in heat death is not empty of energy. It contains all the energy it has ever contained, minus the small amount radiated away in the earliest epochs of its existence. But that energy is distributed with perfect uniformity across a space that is, by this point, unimaginably vast due to billions of years of continued expansion. It is present everywhere and useful nowhere. It is the ultimate expression of the second law of thermodynamics, the law that states that entropy, the measure of disorder, or the dispersal of energy, always increases in a closed system, never decreases, and tends toward a maximum. The heat death is maximum entropy, the end state that the second law of thermodynamics has been pointing toward since the first moment of the Big Bang. Every process that has ever occurred in the universe, every fusion reaction in every star, every chemical reaction in every ocean, every electrical impulse in every nervous system, every computation in every mind, has increased the total entropy of the universe by some amount. Every candle ever lit has pushed the universe infinitesimally closer to this final state. Every heartbeat, every thought, every star that has ever burned, all of it was always moving toward this. Now consider what this means for the concept of time itself. Time in the way we experience it, as a flow, as a direction, as a distinction between past and future, is intimately connected to entropy. The reason the past feels different from the future, the reason you can remember yesterday but not tomorrow, the reason causes precede effects and not the reverse, is rooted in the fact that the universe began in a state of extraordinarily low entropy and has been moving toward higher entropy ever since. The arrow of time points in the direction of increasing entropy. It always has, it always will, but in a universe at maximum entropy, in a universe where entropy can no longer increase because it has already reached its maximum value, what does time mean? In a technical sense, time still exists. The equations of physics do not stop. Particles still have positions and velocities. Space still expands. The laws of nature still apply. But in a practical sense, in any sense that relates to experience or change or the passage of distinguishable moments, time has lost its meaning. A universe at maximum entropy is a universe in which nothing changes, in which no process occurs, in which one moment is identical to the next in every measurable way. The difference between 1 second and 1 trillion years in the heat-death universe is nothing. There is no process whose progress could be used to measure it. There is no clock that could mark it. Clocks require energy gradients to operate. In a universe without energy gradients, there are no clocks. There is no change. There is no before and after. There is only the eternal, unchanging, featureless present of maximum entropy. This is the state the universe is moving toward, has always been moving toward, will reach and then inhabit, not for a long time, but forever. But here is where the story becomes strange in a way that physicists genuinely argue about, a way that keeps cosmologists awake in the small hours of the morning thinking thoughts that have no comfortable resolution. The heat-death universe is not perfectly uniform. It cannot be. Quantum mechanics forbids it. Even in a universe at maximum entropy, even in a space where the average energy density is nearly zero and the temperature is nearly absolute zero, quantum fluctuations still occur. They must. They are not a failure of equilibrium. They are a feature of the quantum vacuum itself, the irreducible minimum of physical activity that cannot be removed even in principle. Virtual particles appear and vanish. Fields fluctuate. The fabric of space-time itself ripples with quantum uncertainty at the Planck scale. These fluctuations are under normal circumstances entirely insignificant. In a universe full of stars and planets and black holes, quantum vacuum, fluctuations are overwhelmed by classical processes on every scale. But in a universe at heat death, a universe where classical processes have ceased entirely, where the only activity is the quantum foam of the vacuum, these fluctuations are all there is. And given enough time in quantities that make even the Google years of black hole evaporation seem brief, something extraordinary becomes possible. In 1896, the Austrian physicist Ludwig Boltzmann proposed a thought experiment that has haunted physics ever since. He asked, in a system at thermodynamic equilibrium given infinite time, is it possible for a spontaneous fluctuation to produce a region of temporarily lower entropy? His answer was yes. In a system at equilibrium, every possible configuration of the system is in principle accessible. Given infinite time, every configuration will eventually occur, including configurations of dramatically lower entropy, including in principle configurations of arbitrarily complex structure. Applied to the heat-death universe, this leads to a deeply unsettling conclusion. Given enough time, and we are speaking of timescales that make a Google look like a Planck time, a random quantum fluctuation could spontaneously produce from the featureless background of maximum entropy a region of locally lower entropy, a region with structure, a region with information. The fluctuation could, with probability that is almost zero, but not quite zero, produce something as complex as a single functional neuron floating in empty space, a structure sometimes called a Boltzmann brain, a conscious observer that spontaneously assembles itself from random fluctuations and exists briefly before dissolving back into the equilibrium background. The timescale for such a fluctuation is approximately 10 to the 10 to the 50th years, a number so large that writing it out in standard notation would require more digits than there are atoms in the observable universe. But in a heat-death universe that lasts forever, even this timescale is not a barrier. It is merely a weight, and the fluctuations do not stop there. Given still more time, timescales that make even the Boltzmann brain timescale look brief, a random fluctuation could spontaneously produce something larger, a cell, an organism, a planet, a solar system, a galaxy. In principle, given truly infinite time, a random fluctuation could reproduce the entire observable universe as it currently exists, every galaxy, every star, every planet, every person as a spontaneous emergence from the quantum background. This possibility, known as a Poincaré recurrence after the French mathematician Henri Poincaré, who first described it in classical systems, is not science fiction. It is a genuine prediction of statistical mechanics applied to a finite system with infinite time. The recurrence timescale for a system as complex as the observable universe is approximately 10 to the 10 to the 122nd years, a number that has no meaningful name, a number that makes every other large number in this story seem like rounding error. But it is not zero, and in an eternal universe, not zero means eventually. The philosophical implications of this are genuinely difficult to navigate. If the universe is eternal and quantum fluctuations are real, then every possible configuration of matter and energy will eventually occur not once, but infinitely many times. Every star that has ever burned will burn again, not through the normal process of stellar formation, but as a spontaneous statistical fluctuation from the vacuum. Every civilization that has ever existed will exist again, assembled by chance from random fluctuations with no memory of anything that came before, because the fluctuation that produces them does not carry the information of previous configurations. This is either the most hopeful or the most disturbing fact in cosmology, depending on your temperament. But there is a competing possibility, one that does not require infinite patience, one that does not rely on fluctuations of incomprehensible rarity, and one that has found renewed interest among cosmologists in the past several decades. The universe may not be eternal, not because it ends in heat death and then nothing, but because the heat death itself may be unstable. The discovery in 1998 that the expansion of the universe is accelerating, driven by what physicists call dark energy, a form of energy intrinsic to empty space, whose nature remains one of the deepest unsolved problems in physics, introduced a new possibility for the ultimate fate of everything. If dark energy is truly constant, if it does not change over time, then the universe will expand, forever cooling into heat death as described. But if dark energy changes, if it increases over time, then the expansion of the universe could accelerate without limit, eventually tearing apart. First the galaxy clusters, then the galaxies themselves, then solar systems, then planets, then molecules, then atoms, then atomic nuclei, then the fundamental particles themselves, in an event called the Big Rip. If the Big Rip occurs, the heat death never arrives. The universe ends not in stillness, but in a final, violent tearing in which the fabric of space-time itself is shredded at a finite time in the future. Estimates for when a Big Rip might occur, if it occurs at all, range from tens of billions of years to hundreds of billions of years, within the same order of magnitude as the remaining lifetime of the stelliferous era. Alternatively, the vacuum state of the universe, the quantum configuration of empty space that underlies all of physics, may not be truly stable. It may be what physicists call a metastable false vacuum sitting in a local energy minimum, but not the global minimum. If that is the case, then somewhere in the universe, at some random point in space, a quantum fluctuation could trigger a transition to the true vacuum, a bubble of lower energy space that expands at the speed of light, rewriting the laws of physics as it goes, annihilating everything in its path without warning. This event, called vacuum decay or the Big Bounce, in some formulations would end the universe not in heat death, but in a phase transition, a rewriting of reality so complete that nothing in the old universe would survive. We do not know if the vacuum is stable. We do not know the precise nature of dark energy. We do not know if the Big Rip awaits us, or the heat death, or the vacuum decay. What we know is that the universe has a fate, that the fate involves an end to the structures we know, and that no matter which pathway the universe takes, the era of stars and planets and life is finite. The heat death, if it comes, is not tragic in the way human deaths are tragic. There is no suffering, there is no loss in the experiential sense, because there is no one to experience the loss. The universe does not mourn its own cooling. The photons drifting through the equilibrium background do not carry grief. The quantum fluctuations of the vacuum are not lonely. The heat death is not something that happens to anyone. It is simply the final state of a physical system that began 13.8 billion years ago in conditions of extraordinary low entropy and has been climbing toward equilibrium ever since. It is, in the most literal sense, the universe coming to rest. The question of whether that rest is peaceful or empty depends entirely on who is asking. And that question, who is asking and what it means that something exists to ask it at all, is precisely what the final chapter of this story is about. 1654, Claude responded. Come back now. Come back now. Come back from the heat death. Come back from the Google years, from the evaporating black holes, from the quantum fluctuations drifting through a featureless equilibrium that will last longer than any number you have ever written. Come back from the Degenerate Era and the dissolving atoms and the cooling white dwarfs. Come back from the death of the last red dwarf, that dim and patient star that burned for trillions of years before finally quietly going dark. Come back to now. Come back to a universe that is 13.8 billion years old, a universe in which stars still burn, in which galaxies still spiral, in which planets orbit, suns and oceans move under skies, and somewhere, on at least one world that we know of, matter has organized itself into structures complex enough to look upward and ask what it all means. Come back to this moment, because this moment seen from the perspective of everything you have just traveled through is almost impossible, not improbable, impossible, or close enough to impossible that the distinction requires a kind of mathematics that has not yet been invented. Consider what the universe has done in 13.8 billion years. It began in a state of near-perfect uniformity, a hot, dense plasma of particles and radiation, smooth to 1 part in 100,000, with only the faintest quantum ripples of density variations seeded across space. Those ripples were the seeds of everything. Gravity amplified them over hundreds of millions of years, pulling matter into filaments and sheets and nodes. The cosmic web that underlies the large-scale structure of the universe today. At the densest nodes of that web, gas collapsed into the first stars, massive, brilliant, short-lived objects that burned for a few million years, and then exploded, seeding the surrounding space with the first heavy elements, the first carbon, the first oxygen, the first iron that the universe had ever contained. those elements dispersed, mixed with new gas clouds, collapsed again into second-generation stars, some of which had enough heavy elements in their surrounding disks to form rocky planets. Around some of those planets, liquid water collected on surfaces kept warm by the light of their suns. In at least one ocean, on at least one planet, chemistry crossed a threshold that has no precise definition, but a recognizable consequence. It began to replicate, to copy itself, to compete for resources, to evolve. 4 billion years of evolution produced, among other things, a nervous system capable of modeling the external world in sufficient detail to predict it, to plan, to imagine futures that have not yet occurred. That nervous system eventually produced language, which allowed the models in one nervous system to be transmitted to another. It produced writing, which allowed those models to persist beyond the lifetime of any individual nervous system. It produced mathematics, which allowed those models to achieve a precision and universality that transcended the particular perspective of any single observer. And it produced eventually the capacity to look at the night sky and not merely see patterns but understand them, to determine from the faint red shifting of distant galaxies that the universe is expanding, to calculate from that expansion that the universe had a beginning, to measure from the cosmic microwave background the conditions of that beginning with extraordinary precision, to predict from the laws of thermodynamics and quantum mechanics and general relativity what the universe will become in a Google years. All of that happened in 13.8 billion years. In the language of cosmological decades, it happened between decade 0 and decade 10, and the entire subsequent history of the universe, the 100 trillion years of the remaining stelliferous era, the incomprehensible depths of the Degenerate Era, the Google years of the black hole era, the eternal stillness of the heat death, all of that will happen without anything like this occurring again. Not because complexity is impossible in those future eras. We have seen that in principle, quantum fluctuations could spontaneously assemble complex structures given sufficient time, but those spontaneously assembled structures would be isolated accidents, Boltzmann brains, flickering briefly into existence and then dissolving with no history, no continuity, no connection to anything that came before. They would not be the product of 4 billion years of evolution, of a planetary system enriched with heavy elements from previous stellar generations of a star, providing a stable energy gradient for billions of years of a universe young enough and energetic enough to support the complexity that life requires. Life, as best we understand it, requires a star. A star is a fountain of low-entropy energy photons streaming from a hot surface into a cold sky, providing the gradient that chemistry can exploit. Without that gradient, without the difference between the warmth of the sun and the coldness of space, photosynthesis cannot occur, metabolisms cannot run, the extraordinary engine of biology cannot turn. Life is at its most fundamental level, a process that captures the energy flowing from hot to cold and uses it to build and maintain ordered structures against the tendency of entropy to dissolve them. And stars are finite. The universe has a window, a period in its history, when stars exist and planets orbit them, and conditions for life as we know it are at least physically possible. That window opened approximately 100 million years after the Big Bang, when the first stars ignited. It will close at cosmological decade 14 when the last red dwarf goes dark. From opening to closing, the window spans approximately 100 trillion years. 100 trillion years sounds enormous, and measured against a human lifetime it is. Measured against recorded history, it is unimaginable. But measured against the total duration of the universe, measured against the Google years that follow it, is a flash. It is the first frame of a film so long that the entire window of stellar existence occupies less time than the shutter takes to open and close. We are in that frame. Right now in this moment, as you read these words or hear them spoken, the universe is in the only era it will ever know in which the conditions for complexity, for life, for consciousness, for the asking of questions about the fate of everything are physically present. We did not arrive early to a party that has not yet begun. We did not arrive late to a party that has already ended. We arrived by some combination of physical law and chance, and the extraordinary patience of 4 billion years of evolution at precisely the window. The only window. This fact has a name in philosophy and cosmology. It is called the anthropic principle, the observation that the universe we observe must be compatible with the existence of observers, because if it were not, we would not be here to observe it. In its weak form, it is almost tautological. Of course, we find ourselves in conditions compatible with our existence. We could not find ourselves anywhere else. But in its stronger implications, it points towards something genuinely astonishing, that the conditions required for minds to exist are extraordinarily specific, extraordinarily temporary, and extraordinarily fragile on cosmic timescales. The universe did not have to produce minds. It did not have to produce stars of the right mass and longevity. It did not have to produce rocky planets at the right distances. It did not have to produce oceans or atmospheres or the particular chemistry of carbon. It did not have to produce evolution or nervous systems or language or mathematics. All of these things emerge from physical laws that do not seem to have minds as their goal, from processes that are indifferent to whether any observer ever exists. And yet, here we are, 13.8 billion years after the beginning, in the midst of the only era that could have produced us, on a planet orbiting a middle-aged star in the outer reaches of a galaxy that is itself one of roughly 2 trillion galaxies in the observable universe, aware, curious, capable of looking at the sky and asking not merely what is there, but what will become of it, and what it means that something exists to ask. There is a particular quality to this moment that becomes visible only from the perspective of deep time, the perspective you now carry, having traveled through the death of stars and the evaporation of black holes and the stillness of maximum entropy. From that perspective, the present moment looks different, not smaller, not less significant, larger, more extraordinary, more improbable, more luminous. Every star in the night sky is burning right now. Every one of them is converting hydrogen into helium, releasing energy that has traveled across light years to arrive at your eyes as a point of light. That light is not ancient and dead. It is current. It is the present tense activity of a universe still in its productive phase, still generating the gradients and the complexity and the warmth that make experience possible. Every element heavier than hydrogen and helium in your body, every carbon atom in your cells, every oxygen atom in your blood, every calcium atom in your sheer bones, every iron atom at the center of every hemoglobin molecule was forged in the interior of a star that died before our solar system formed, or in the collision of neutron stars whose merger scattered heavy elements into the gas cloud that eventually collapsed to form the sun and the earth and you. You are not watching the universe from outside. You are made of it. The atoms in your body have been part of stars. They have been part of gas clouds. They have been part of oceans and rocks and other organisms across billions of years of Earth's history. They are on loan to you for the brief duration of your life, and when that life ends, they will return to the cycle, to the soil, to the ocean, to the atmosphere, eventually perhaps to space, eventually perhaps to a new star forming from a new gas cloud in the distant future of the stelliferous era. You are not a witness to the universe's history. You are a continuation of it, and that continuation is temporary in ways that operate on every scale simultaneously. Your individual life is temporary, your civilization is temporary, your species is temporary. Your planet is temporary. The sun will eventually expand and sterilize it, or the expansion of the universe will cool it below the possibility of life long before then. The stars are temporary. The stelliferous era is temporary. Even the black holes are temporary. The only thing that is not temporary is the universe itself, and the universe's permanence is precisely the heat death, the state of maximum entropy in which nothing changes, in which there is no story left to tell, in which the words temporary and permanent lose their distinction because there is no process by which one moment can be distinguished from the next. The universe is permanent only in the sense that it will persist forever in a state indistinguishable from nothing. And you, temporary, fragile, made of borrowed atoms alive on a small planet in the outer arm of an unremarkable galaxy, in the middle of the only era that could have produced you, you are the universe's way of knowing itself, not metaphorically, literally. The information encoded in your brain, the models of the external world that your nervous system has constructed over a lifetime of experience and learning, represent the universe reflecting on its own nature, with the only instrument capable of doing so, a mind. The universe does not know it exists. It cannot. Existence requires no witness, but you can know that it exists. You can know its age and its structure and its fate. You can calculate what it will become in a Google years. You can trace the path from the Big Bang to the heat death, and understand at least in broad outline the arc of everything. That capacity to understand, to trace the arc, to ask the question, is the most improbable thing the universe has ever produced. More improbable than the first star. More improbable than the first cell. More improbable than the extraordinary chain of contingencies that led from the Big Bang to this moment. Because all of those things could in principle have happened without anyone ever noticing. The stars could have burned and died in silence forever, with no mind to observe them, no mathematics to describe them, no language to carry their story forward. They did not. You are here, reading these words or hearing them, carrying in your mind for the duration of this moment the arc of everything from the ignition of the first stars to the evaporation of the last black hole to the eternal stillness of maximum entropy. That is not nothing. That is from the perspective of everything that will ever exist, almost everything. The universe is 13.8 billion years old, and it has spent that entire time building toward the capacity for this moment. Not intentionally, not with purpose, but through the patient operation of physical laws that happen in the patient physical laws. Particular configuration of this universe to permit complexity. The stelliferous era will continue for another 100 trillion years, and in that time, there may be other minds on other worlds, orbiting other stars, asking the same questions, tracing the same arc. Or there may not be. We do not know. The silence we have received from the cosmos so far suggests that minds are rare, perhaps extraordinarily rare, perhaps rare enough that the nearest one is beyond reach, even at the speed of light. If that is true, if we are alone or nearly alone in the stelliferous era, then the significance of this moment deepens still further. The universe's capacity for self-knowledge, which required 13.8 billion years, and the deaths of countless stars and the extraordinary accident of life on Earth to produce, may be present in only the rarest plus. The light that carries the story of the cosmos may have very few minds to receive it, which means that the light falling on you right now, the starlight, the sunlight, the faint microwave glow of the Big Bang itself still washing over the Earth after 13.8 billion years of travel, is not wasted on you. It is received. It is understood, or at least understood in part, to the extent that any mind can understand the universe that contains it. And that understanding, however incomplete, however temporary, is the universe's most extraordinary achievement. Look up when next you have the opportunity at the night sky. You will see stars, points of light at various distances burning with various intensities at various stages of their lives. Some of them are young, some are old, some have planets. Some of those planets may have oceans. Some of those oceans may have life. All of those stars are burning in the stelliferous era, the only era, the window. Somewhere beyond what you can see, the last red dwarfs are burning dim, patient, miserly, with their fuel destined to outlast everything else by trillions of years. And beyond them, in the deep future that you have now traveled through, the white dwarfs are cooling, the black holes are evaporating, the last gamma rays are spreading through the equilibrium background, and the universe is settling with the patience of eternity into its final rest. All of that is coming. All of it is as inevitable as the second law of thermodynamics, which has never in the entire history of the universe been violated even once. But it has not come yet. Right now the stars are burning. Right now the universe is alive with fire and light, and the extraordinary, improbable, temporary complexity that physical law permits in this narrow window of cosmic time. Right now, you are here. That is not a small thing. Placed against the background of a Google years of darkness, placed against the heat death and the evaporating black holes and the dissolving atoms, the fact that right now, in this moment, on this world, under these stars, something exists, can trace the entire arc from beginning to end, that can hold the whole story in mind and feel the weight of it, that can look at the dying universe and understand what it is looking at. That is the brightest thing the universe has ever made. Not the most energetic, not the most massive, not the longest lasting, the brightest. A single candle of awareness burning in a darkness that will stretch for longer than numbers can honestly describe. Lit by the energy of a middle-aged star, fed by the atoms of dead stars, carried by a mind that will last in cosmic terms for less than an instant, and yet it burns. Right now it burns. That is enough. That is extraordinary. That is from the perspective of everything that comes after almost everything that will ever matter. The stars are still here, and so are you.